So we've looked at consistent independent systems where there's one solution. And then we've looked at inconsistent systems where there's no solution, parallel lines. And the last one that we want to look at is a consistent system as well, but what we call it is a dependent system. So the reason is this because there are infinitely many solutions. And you can assume that if there are infinitely many solutions, and this is where the two lines intersect, that they must be equivalent. So let's look at this system here. If we were to solve for y for both of these and graph these, or if we were to graph them on the graphing calculator. So let's look at the first one, and if we solve for y, we would bring the x over here. We have 3 minus x, and then we would have to divide everything by 4. So we would have y equals 3/4 minus x over 4. And then for the second one, we could just divide everything by 4, and we're left with y equals 3/4 minus x over 4. So we actually have equivalent equations here. And if you can recognize that just by looking at this system, if you can recognize that quickly, then that's fantastic because you can immediately tell that it is a dependent system and there are going to be infinitely many solutions. So we can graph this really quickly if we just set our y-intercept to be 3/4, and then we have a slope of negative 1/4. So that means we're going down 1 and to the right 4. 1, 2, 3, 4. And then we can draw a line between these 2 points. Oh, it's pretty close. And then this is going to be the same line as the next line, which means there are infinitely many solutions, or a dependent system. Okay, so we did do a bit of rearranging to figure that out. Now, we've only looked at really graphing to figure out the solutions to these equations, systems of equations, but there are other ways. And one of those ways, and people refer to it many times as solving it algebraically. I don't know if this is completely the best way to explain that, solving it algebraically or solving it logically. It's more of a system to determine how to solve the system. So let's look at one of these methods, and we call it elimination. So we're solving a system of equations using elimination. So say that we're given some system, and let's just pick, let's see here, if we're given 3u plus 3v is equal to 15. And then our second equation is negative 2u plus 3v is equal to negative 5. Okay, so here we have our system of equations, and we're trying to figure out where these two equations actually intersect. So let's try to determine that by determining what v and u are. Well, if we're going to try to figure out what v and u are, and there are 2 variables per equation, we need to eliminate a variable to solve for one, and then we can plug back in. So the way that we're going to do that is we're actually going to combine the 2 equations. But before we do that, we want to make sure that when we combine the 2 equations, that something's going to cancel out. So first what I'm going to do is multiply this entire second equation by negative 1. So if I multiply the entire equation by negative 1, it doesn't change the equation. So I can rewrite this now as 2u minus 3v equals 5. Then I can bring the first equation back down, and I have 3u plus 3v equals 15. All right, well now I have a negative 3v and a positive 3v. I know if I combine these two equations now, those will cancel, and I'll be left with a 5u equals 20. So u equals 4. So now I have a numerical representation of u. So now all I can do is take this and plug it back in pretty much anywhere. We can pick the first equation because it's all positive numbers. And if I do that, I get 3 times 4, that's u, plus 3v equals 15. Well, that's 12. If I subtract that to the other side, I'm going to get 3v equals 3. And then if I divide by 3 on both sides, I get v equals 1. So my u comma v solution would be 4 comma 1. And there we are. That's elimination. The only other I'm not going to get into it right now, actually. I'll make it in the next video.